All right, so today we're going to be doing 4.6a, which is related rates, part 1, day 2. So the equations, the rules, the instructions, the guidelines are all the same, but we're going to go into depth with some of these that we haven't addressed yet. All right, so we're looking at a problem here. It says a cylinder filled with water has a 3-foot radius and a 10-foot height. It is drained such that the depth of the water is decreasing at a rate of 0.1 feet per second. How fast is the water draining from the tank? So we have a formula to represent volume of a cylinder, and that would be pi r squared h. So we're going to have to utilize this here, but before we do that, we have to think through this problem. So basically, the height is going to be the height of the cylinder if it's filled to its capacity, correct? When it's filled to its capacity, its height is 10, but as the water drains out, what's happening to the height of the water line?
It's going down.
Yeah, it's no longer going to be the same as the height of the actual container, correct? So it's decreasing. But as it decreases, does the radius change at all in this problem? No, because even withstanding, if you run out of water at the very end, you're still going to have the same radius. So the radius we could say is what?
3.
90.
Or
You're right, it is 3, but
constant
a
change.
constant. Yeah, exactly. So the radius is constant, okay? We know that things, when they're constant, we don't have to find their rate of change, correct? Because they're constant. So that's one of those variables that you can actually plug in before you take
The derivative.
the derivative. Now, it's really, really important that you know when to plug in before, because had you not done that, you would take the derivative here. You would have to use the product rule, okay? You're going to end up with a dr dt and a dh dt and an r and possibly an h. If you don't have all those variables to solve for, now you have more variables than you can solve for possible. So then you end up with a situation that's not solvable sometimes. So that's why it's important to know when to plug in early. It's going to make your life easier in the end. So right now, we can say that we know that the volume of a cylinder is equal to pi 3 squared times h, correct?
Yeah.
Of this particular cylinder, because we know that its radius is never going to change. Okay, so we're here. Now we're going to go through and address what we know and what we want to know. So this right here, this is a rate, correct? It's going to be a d something over dt, correct? Which rate is that in particular?
Height.
It's the rate of the height, correct? It's the rate at which the height changes. Not only that, it happens to be changing, but is it negative or positive?
Negative.
Negative, because it's going down. Now, if you forget about this step, which I sometimes do, you can always just negate in the end. Okay, it's not a huge deal. It's not going to change any of the math or anything like that. So that would be the rate at which my height changes. We have our current height, and then really that's all we have, but we want to figure out how fast the water is draining from the tank. Is that a rate or a value?
Height.
That's a rate.
It's a rate. It's the rate of which what changes?
Height.
Not the height,
Volume.
the volume. How fast water is draining from a tank, the volume is what's changing. The volume of the cylinder is how much it's filled up with, correct? So if it's changing, that's what's happening when it leaves. So we're trying to figure this out, okay? So to do that, we're going to take the derivative of this formula now. Bless you. So the derivative of this is going to be what?
90 pi.
dv over dt.
Yep, equals, you're right, 9 pi, but times, when we take the derivative of h in terms of t, it's going to be times dh over over dt. So now we can plug in what we know, which is this right here, correct? So that's going to be dv dt equals 9 pi times negative 0.1 feet per second. And our units kind of got messed up here because we technically had a radius, so this is technically feet squared if you want to be technical here. So it's going to give me dv dt equals negative 0.9 pi feet cubed per second. So if you like to hold your variables out through the whole thing, you can, or you can throw them in at the end. Of course, we know that volume is always cubed, and then this is per time, so it's going to be whatever over whatever time frame we're using, seconds, minutes, hours. So does anybody have any questions about how we did this one? So do you understand
Is that the final answer?
that's the final answer.
Okay.
So do you understand the concept of when to plug in before taking the derivative?
Yeah.
Or hopefully you're starting to understand. Okay. So Next question is a cone problem. Gravel is dumped from a conveyor belt at a rate of 30 feet cubed per minute. So right off the bat, I know this is a what? Is it a rate or a value?
It's a rate.
It's a rate of which what changes?
Your
It's cubed, so it's going to be
volume.
volume. It's the rate at which the volume changes. And it forms a pile in the shape of a cone. So with these cone problems, they're going to have to give you this piece of information here. Sometimes they use numbers, sometimes they just use descriptors, okay? Sometimes you're going to end up with extra numbers and be like, well, where does this come into play? This tells you how the relationship between the radius and the height. They have to tell you something to do with that, because let's think about this logically for a second. At the very bottom of the cone, or the top if it were flipped upside down, we have a set radius and a set height, correct? But as time goes on, if this were to fill or go down or up, the radius is going to get smaller and smaller, correct? Unlike with the cylinder, see how the radius stays the same throughout the whole thing? But with a cone, the radius shrinks, correct? As the height shrinks. Now, every time this happens in a cone, the radius and the height are proportional to each other in some way or another, okay? So they always have some kind of set proportion. So they tell us something about that proportion in this problem, and that's necessary to figure out what the problem is. So, base diameter and height are always the same. So they're telling me that the diameter is always equal to the height at any given moment. Now here's the problem. Does this formula involve diameter at all? No, but we know that diameter is equal to what?
2R.
2r. Now, before we get into anything else, we have to think about what the question's asking for, because we're going to plug in to only end up with one variable. We just need to figure out which variable we should plug in for. So, how fast is the height of the pile increasing? Is that asking for the rate of the height or the rate of the radius?
The rate of the height.
The rate of the height, correct. So we want to know what the rate of the height is. When the pile is 10 feet high, that's a value or a rate?
Value.
That's the height. Good. So we're going to have to solve to get radius equal to whatever this is, so we can plug it in and only have height left in our formula. We want to get rid of the radius in the formula. So how can I solve this to get radius equal something?
H in for 10. Or
Well,
10 for H.
we don't want to plug any values in necessarily. We just want to get radius in terms of height, so it would be...
Divide height by 2.
Yes, exactly. So the radius is always equal to the height divided by 2 at any given moment. So if I know what the radius is, I can find the height or vice versa. Okay? So now that I know what the radius is equal to, I can replace r in the formula with r, or pi over h over 2. There we go. So this is going to be v equals 1/3 pi radius squared h. Okay. That's going to be v equals 1/3 pi times
H squared over 4.
h squared over 4 times
H.
h. And then this all simplifies down to pi over 12 times h cubed, correct? Okay. So the benefit of this and the reasoning for this, if I were to have tried to take the derivative here with the height and the radius, we have to use product rule. And then I don't even know if I know what the rate of the height is to plug it in. Yes, Brandon?
It's just, you wrote it weird to me. Like, why is, I mean, I guess it doesn't matter, but if the H not being, like, up there with the 12 just looks weird.
Oh, well, h would be with the pi.
I know.
Okay.
It just looks weird.
Oh, I'm sorry.
Yeah, it threw me off too.
Usually, when you're dealing with derivatives, I like to get my constant away from the variable, just because it's easier. So now, we're at the point where now we can take the derivative of this, correct? And we don't have to use any product rule. So what would be the derivative of this?
dv over dt
Good.
Pi,
equals
pi, the 4.
Pi over 4, yep.
H.
H squared times
dh over dt.
dh over dt. So you might have just put the 3 out first, and then what happens is pi over 12 times 3 ends up being pi over 4. So that's just algebra stuff. So we get here, and now we're ready to plug in what we know. So we know what,
H is 10.
we know h is 10, and we also know something else. We know what dv dt is, correct? So we can plug in for those two items. I'm not going to use any units. I'm going to put them in at the end. So this becomes 100. What's 100 divided by 4?
25.
So I end up with 25 pi times dh dt,
Equals 30 feet per minute.
which is 30 over pi times 25 equals dh dt, correct?
Okay.
You with me?
Can you take out 5?
Yeah, exactly. So we can reduce this, which should become 6 over 5 pi, correct?
Yeah.
So it's going to be 6 over 5 pi, and that would be, what's the units on this? Feet per what?
Cubed? Or minute?
Feet per minute, yeah, and it's not cubed because this is just regular height.
Uh,
So volume is cubed, area is squared, heights, radius, all that stuff are just regular.
that's no-
So if you do plug in your units from the beginning and follow through with them, it will work out. So if that ever confuses you, you can do that. So the homework you're going to get, first question's a sphere. The reason I gave you a sphere problem in this is because it's more similar to the ones we did on Friday. But I want you to be able to see a mixture of these together so you're able to know when you're plugging in constants versus when you're not plugging in constants. I want you to focus on practicing that concept today. Okay, when I plug in before versus when I plug in later. That's such an important concept in this particular topic. So that's what you guys are going to focus on today.